Basic probability and simulations. Outcomes are governed by chance, but in many repetitions, a pattern is going to emerge. And the big thing that I'm going to point out here is in many repetitions. So we are going to talk about today long run behavior versus short run behavior and how the probabilities change if you're doing something a couple of times versus something a million times. So similar to our sampling frame, when we were selecting experiments and sample surveys, we have a list of all of the possible outcomes. So we're going to write out a sample space for flipping a coin in just a second, but you want to make sure that all of the possibilities for what could come from your random event are listed. Now, in a perfect world, every single question that you get would have the capability to be able to list out the entire sample space, but sometimes what you're doing is too large. So say, for instance, you're flipping a coin 5 times. Well, that's going to be a really, really large sample space, like 32 possible outcomes. And realistically, it's kind of hard to list all of those out in the time frame that you get for, say, a multiple choice question.
Eagles, just want to take a quick second to remind everyone that Captain Lawrence sent an email with a list of students that will be taking the ASVAB test this morning. At this time, please check that list. Any student supposed to take the ASVAB test this morning should head to the freshman gym at this time. Happy Monday. It's going to be a great week. A lot of exciting things going on.
I think you take all your stuff with you. Yeah, I imagine you probably won't be back this period. Okay, so an event is going to be a specific desired outcome or set of outcomes. Now, in the set of outcomes, when I was mentioning picking a marble out of the bag and you want a red one and a blue one, both of those would have their own individual probabilities. And for the most part, we go in and we multiply those things together. Now, notation, something you are familiar with already. A lot of the time on the directions for your test questions, you'll see it say you have to include a probability statement. This is a probability statement where it's saying the probability of event A occurring. Now, I will kind of give you that disclaimer grading-wise for the test. Whenever you guys took the normal distribution test, I told you you had to have a probability statement or a sketch. Now, in the case of probability, you don't have the option for a sketch, so you have to include something indicating what you are looking for. So it doesn't always have to be you're assigning it a letter, but you can put in the word. So if I want a red marble, I can do probability of red. And that's enough to tell me what you're looking for. Okay, range of probabilities. So the probability of an event is between 0 and 1. This is a big key idea because sometimes they'll give you a question that is as simple as, is this a valid probability distribution? And there's 2 things you're checking. 1, you're checking to make sure that all of the probabilities listed are between 0 and 1. What that means is they can't be over 1. 1.10, there's no 110% chance of something happening. They can't be negative. You don't have a negative % chance of something happening. So they have to be between 0 and positive 1. And then the second thing that you are checking is all probabilities must add to 1. So if you go in and you're checking if this is a valid probability distribution, that's just a fancy way of saying a list of all the probabilities in this scenario, and I take all of them and I add them together, it has to be equal to 1. Now, if it's over 1, it's not a valid probability distribution. If it's under 1, it's not a valid probability distribution. The only time it's okay for it to be under 1 with the values that they list for you is if they want you to find the missing probability. In that case, yes, you're just going in and you're seeing what's missing to get us to 1. But if they said these are all of the probabilities we have and it does not total to 100%, which is 1, it's not valid. So between 0, 1, and up to 1 when you add them all together. Has to be equal. Okay, so this is a bunch of just terminology you might see. We discussed the differences between, well, we did not, but we are going to talk about them now. We're going to talk about the theoretical probability and the empirical probability. So this is where I came in and I said we have two possibilities for what could be occurring. We could have something that's in the long run behavior, or we can have something that's in the short run. So I'm going to use my classic example of a coin. If I ask you what's the probability of getting heads when I flip a coin, what would you tell me? 50%, right? Because there's two sides of the coin. There's one side that is heads. So that is measuring our long run behavior by taking the number of desired outcomes, so in our case, heads, and dividing it by the number of total outcomes. So for the coin, there's two possibilities for what you could get, heads or tails. We're only interested in heads. That's why it's 1/2. That's why it's 50%. Now, that is long run behavior. That is theoretical probability where, in theory, over time, this is what should occur. You should get heads 50% of the time. Now, short run behavior is a little bit different because if I actually take my coin and I flip it 10 times, am I guaranteed to get 5 heads every single time I flip it? No. So short run behavior is a little bit different. It just takes your number of successes and it divides it by your number of trials. Now, a lot of the time, when you look at short run behavior, it's not going to match. Even if I went in and flipped my coin 100 times, I'm not going to get 50 heads, 50 tails. You might get something a little bit closer than what you would do if it was 10, but it's not going to be perfect. But what happens when we take that coin and we flip it 1,000,000 times, you're going to get closer and closer and closer to that 50-50 split. And this is because of something we refer to as the law of large numbers. Basically, with the law of large numbers, you're going to take your simulated, your empirical probabilities, and they're going to get closer to the theoretical probability as the number of trials increases. So as you start to do things more and more and more, you're going to get closer to that actual probability. Now, for us, when it comes to heads and tails, we know that it should be 50%. But this law is a little bit nicer when it comes to things where you're not necessarily so sure what the probability is. So say, for instance, you have a bucket of marbles, my classic example. We've got red marbles, we've got blue marbles. And then I'm going in and I want to see, well, what's the probability of getting a red marble from this big bucket? I can go in and pick a bunch at a time and see what those probabilities are. But as I do it, as I collect more and more and more, it's going to give me a better idea of what that actual probability is without having to go in and count all of them. So just to kind of talk general probability, I'm sure you all know this. Basically, if our probability is 0, the event will not occur. Guaranteed. If it's all the way at 0, it's not happening. If the event is the probability of an event is at 1, it is guaranteed that the event will occur. Basically, if you see I have a 100% chance of rain, it's going to rain. Guaranteed. Now, if you have a 0% chance, probably not going to rain. Now, in the middle, we kind of talk about if it's a 0.5% chance, the event is equally likely. And then I just say anything between 0.5 and 1 is more likely, and then less likely on the other side. What you will kind of find is a lot of these questions are going to ask you, given all of these parameters in this situation, do you think the probability that they are claiming is correct? Or do you think it's suspicious? Or do you think that they are lying? And so something to kind of pull this back to what we did with normal distributions is we had a threshold where if it was below this number, we said it was unusual, it seemed weird, like what they're saying isn't actually true from what I'm seeing. And so if the probability is less than 5%, and this equates to being outside of 2 standard deviations. So the same idea we did in Unit 1. If the probability is less than 5%, then it is considered unusual. And this is going to be our threshold of if I go in and I simulate something and I try to see if the claim that there's 60% red marbles, 40% blue marbles, and I go in and I try to get the probability of making those selections, and it's only a 2% chance of it happening, then it's unusual. I would think that their claim of it being 60-40 is incorrect. So the threshold is going to be 5%. If it's below 5%, it's weird, we disagree, we don't think that what they're saying is correct. If it's above 5%, it probably happened randomly. The only thing that I'll add on here, and we'll talk about it in a second when we're actually writing some answers out, they kind of give you an option for how you can put your answers. You can either leave it as a decimal or you can turn it into a percentage. I believe on my test, I say to turn it to a decimal, but I think I'm going to change it so you can have either one. But one thing about this is we are going to round to 4 decimal places, simply because in the conversion of a decimal to a percentage, I need to make sure that I am not rounding to a whole number. Usually rounding to a whole number is a little bit too decisive. So I try to keep some decimals there, which I'll show you in just a second. So let's go to example 1. All of the examples today are not super complicated, pretty easy, basic probability. Again, I have a bag. It contains 10 marbles, 2 black, 3 blue, 1 red, and 4 white. What is the probability you will pull out a white marble? So you have the option of going in and assigning a letter to each event. Personally, even me as your teacher, I don't do it all of the time, unless it's like really long and I know I'm not going to want to write it over and over and over again. I just put the word inside of my probability statement. And I'm going to get this question more times than I would like, but whenever I ask you for a probability statement, this is all I'm talking about. I just need something where you're telling me what you are looking for. So in this case, white. It doesn't even have to be specific in terms of like, it needs to say white marble. I just need to know what are you actually trying to find. Now, in this case, there are a total of 10 marbles in the bag. So that's my denominator. And 4 of them are white. I like to include questions like this because here's where I come in and I talk about partial credit. Whenever I grade your tests, I know you probably could have looked at what we have and seen that it's 4 out of 10, 40%. You know what it was. You just want to write 0.4, which is great. Truly, it's the correct answer. It will work out. However, I will say, I think that it's better for you to include your fraction simply because I have written on many tests calc error question mark because all of the work that you have is correct, but somehow you got the wrong answer. So it might have been something that was mistyped. It might have been something where you put it into the wrong function, but in the end, you didn't get the actual correct answer. Now, for a person that shows their work, so they showed me that they had 4 out of 10 set up, I can give that partial credit. I can say, okay, they at least knew what they were doing. Something must have went wrong when they jumped to the calculator. However, if I just see probability of white is 0.45%, and that's all you have, I can't give you credit for that. So yes, it's okay. I would say in my best piece of advice is even when you know it's a simple answer, give me as much as I can see to award you partial credit. Now, on the AP exam, they're not like broken down into like this gets a point, this gets a point, that gets a point. It's more of a kind of holistic approach, but I need to kind of see how you set these things up. So one other note here, I tell you that you can kind of write anything in terms of whether it be a decimal or a percentage. If the question specifies that they want a percentage or a proportion, you have to write it in the way that it indicates. So if they say proportion, they want a decimal. If they say percentage, they want a percentage. One of these things to be very careful for is on your math lab. Sometimes the blanks will have a percentage after it, and if you put it in as a decimal, it's going to tell you it's wrong. It's going to tell you it's wrong and tell you it's wrong until you notice that the percentage sign is there. So just be careful. Part B, what is the probability you will pull out a blue marble? Same idea. I'm just going to go in. There's 3 blue marbles, 10 marbles total, so I can say 0.30 or 30%. Now I'm writing out both answers. If you don't have a question, or if you have a question that doesn't indicate one or the other, both of these are acceptable. So you can leave it as a decimal or you can turn it into a percentage, and that would be okay. So just to keep that in mind, I will have both answers. You don't necessarily have to have both of them. Any questions so far? Very basic. Sweet. Let's go into, in the spinner below, each wedge is equal in area. What is the probability? So I'm going to write my probability statement that it's going to land on a red wedge. And it looks like there are 8 wedges total and 2 of them, 2 of them are red. So 2 out of 8 is 1/4, and that's going to give me 0.25 or 25%. And for the second part, probability of getting a yellow wedge, 1, 2, 3 out of 8, and I believe that's 0.375, and that's going to turn into 37.5%. So mostly I keep these very easy ones in here just to kind of show you the general layout for what is expected when you get FRQ questions. Give me a probability statement, give me your fraction setup, and give me your decimal or percentage. And that's where I can kind of give you partial credit if something were to go wrong on the calculator side of things. For the most part, in the first half of this unit, you're not going to use your calculator as like a calculator function calculator. It's going to be more just basic algebra. So fractions, decimals, multiplying, adding, things like that. Second half, there's calculator functions that will kind of help you there. So let's go in and let's talk complement, which is something we've already talked about. Probability an event does not occur. A complement. Now, I know in calculus, I believe you also can use A prime. That is probably something, or that is something they will accept on the AP exam. But for the most part, I don't even use this notation. I just go in and I write not A. So again, stats is not super picky about what you say, as long as you are conveying what you are actually looking for. So you can use the notation, or you can just say not this. The probability that an event does not occur is the probability of A complement is 1 minus the probability of A. So that is the same thing as 1 minus the probability event A occurs. Because if I want not A, then I need the probability of A occurring, and everything should total to 100%. So when everything totals to 100%, together, they equal 1. Now, in some cases, it is easier to find the complement of an event than it is to find the event itself, especially when you're dealing with a lot of different probabilities. Like if there's 6 things that could happen and I just want the probability that it's not this one, instead of going in and adding all of the other ones together, you can just do 1 minus the event that you're trying to avoid. So in our case, a coin is flipped 3 times and the results of each flip is noted. Draw the sample space for the event. So whenever you're listing out a sample space, we'll kind of talk about how to calculate how many outcomes there are first. We have a coin. So a coin has 2 sides, heads, tails, typically. And they are flipping this coin 3 times, and the results of each flip is noted. So the first coin that they have has 2 possible outcomes. The second coin that they have has 2 possible outcomes. The third coin, or it could be the same coin being flipped 3 times, but the third flip has 2 possible outcomes. So whenever you're trying to figure out how many combinations of outcomes you have total, all you have to do, it's almost like calculating treatments from an experiment. You just have to multiply them together. So in this case, when I go to list out this sample space, I should have 8 outcomes total. Now, just to kind of put that in a different frame of mind, if I am flipping a coin and rolling a die, a 6-sided die, I would do 2 times 6, and there should be 12 possible combinations for outcomes that I could get from those 2 random events. So in this case, when I go to list out my sample space, I know I need 8 different combinations of things. So I'm going to start off with my heads. So I'm going to have heads, heads, heads. Easy one first. And what I do is I typically just come in and I change 1 at a time. So I know that the other option is tails. So I'm going to say, okay, let's do tails, heads, heads, and then maybe heads, tails, heads, and then heads, heads, tails. Now, I do it this way. You could also do what we call a tree diagram where you have like branches, like heads, tails, heads, tails, heads, tails, heads, tails, and get all of the possible combinations that way. But usually with coin flips, it's not too bad to kind of figure out what the different combinations are. They're not going to make you list out a sample space that is insanely large. Like they're not going to say, we're flipping this coin 10 times, write out the sample space for the 10 coin flips. I don't think that that would be something that you would see on the AP exam because that would just take up too much time. So I'm going to go in and basically I'm repeating the same exact kind of pattern I made in my first column and just flipping it where instead of that being heads, it's now tails. And so in total, I get 8 possible outcomes. Now, one thing about these random events, the order of them is going to kind of change the outcome. So yes, I know if I'm looking at the first column, row 2 and row 3, they have the same number of heads and the same number of tails. But because they occurred in a different order, that is a whole new outcome. So don't think of it as like, I'm just interested in heads, tails, tails, but we're interested in what order do those things occur in. So first question, what is the probability a series of 3 flips will produce exactly 1 head? So I want 1 head only. I know that there are 8 possible outcomes from my sample space. So that's going to be my denominator. And all I'm going to do is go in and look at all of my options and see which ones only have 1 heads. So I don't want 0. I don't want 3. I don't want 2. I just want 1 head only. And if I look at my sample space, there are 3 outcomes that result in 1 heads only. So that's going to be 0.375, and that is going to be 37.5%. And again, any question that just says, what is the probability? You can write in either way. I will say, I don't think we do it this lesson. I think we do it next lesson where we start to interpret these probabilities. Usually the percentage makes a little more sense in a sentence. So, because you can say like, there's a 50% chance that this would happen versus there's a 0.375 probability. It just makes more sense when you convert it to a percentage if you have to interpret. Okay, now the next piece, very important. What is the probability that a series of 3 flips will produce at least one head? So at least one head means it could be 1, it could be 2, and it could be 3, because it's 1 or more. And so I want all of the combinations where this is what I'm seeing, 1, 2, or 3. Now, just to kind of give you a general formula, this is one of the most commonly missed questions on the AP exam, on tests in this class. It's just one that a lot of people struggle with. The probability of at least 1, the easiest way to calculate that is 1 minus the probability of none. And if you have a different colored pen or a highlighter or something, I would make sure that this is kind of known. And I think I include it in a couple of sets of notes that we see in this first half. But basically, I'm going to kind of frame it outside of this question. This question, fairly easy. We have all of our sample space listed. We can go in and see how many of them have at least 1, 2, or 3, and we can count them. But in some questions that they will ask you, it's not going to be so easy. So think of the fact that they may give you a question that says there's a 40% chance of rain today, and they want to know, or rain for each day of this week. And then they want to know what's the probability that there's at least one chance of one of the days having rain. And so because of all of those different individual probabilities and all of the different combinations, sometimes it gets to be too large. And so the easiest way to think of it is the only time at least one isn't happening is when there's nothing at all, like no occurrence whatsoever. And so since everything has to total up to 100%, we can just find the complement of it. So in this case, if I want the probability of at least one head, I can do 1 minus the probability of no heads. And the only time that no heads occurs is when we have tails, tails, tails. And so that is going to be 1 out of 8, which is 7 out of 8, which is 0.875, 87.5%. Now, that is not to say that you could not still just go in and look at all of the outcomes and see that, okay, I know that the first one has a heads, the second one has a heads, the third one, the fourth one, the fifth one, the sixth one, the seventh one. So 7 out of 8 have at least one head in them and gotten the same exact answer. It also works that way. It's just this formula is useful in those cases where you can't list all of the outcomes. And you'll see more questions like that when we start to get to problems where it's like there's a 30% chance that a person is majoring in math and a 20% chance that they live on campus. And you start to get things where it's not something that you can actually list the sample space out for. So for now, it's very doable to just do it in the sense of looking at the sample space, picking out your numbers, but this will be helpful in the future. Yes, Zoe?
I know you said that showing your work helps you get partial credit if you get the answer wrong.
Mm-hmm.
What if you get the answer right? Do you still show all your...
I'm going to ask on the test that you still show your fraction. It doesn't have to be like, if you do it the other way and you only wrote 7 out of 8, that's fine. But if you do it this way and you wrote both of them, I just need something to see. So on your test directions, I believe it says like include a probability statement, your fraction setup, and your answer. So it will be on the directions. I'm going to ask for it just to avoid my conflicts of people who are like, I knew what I was doing, and then it's just a wrong answer. Better safe than sorry. Okay, the last piece of information on this page is the law of averages. So very basic, nothing crazy. Think of all the people you know, or maybe you don't know anyone, who has like 5 kids and they're all boys. And they're like, okay, we're going to have another kid because I want to have a girl, because I want a boy and a girl. So I'm going to try again. And since I've had 5 boys, I should have a girl. The likelihood of me having a girl is higher. In reality, probabilities don't change based on past behavior. So just because this person has had 5 boys in a row doesn't increase their chances of having a girl. It's still a 50-50 chance of boy versus girl. The same thing can be said for like sports teams. Your team has lost 8 games in a row. And you're like, man, we've lost 8 games in a row, so our chances of winning have to be higher because we've lost 8 times in a row. And that's not true. Your chances of winning and losing is the same as it was on game 1. So what that is referred to as the law of averages. So anytime you see a question where they're phrasing it in a way, and we've seen this on multiple choice, and they're saying it hasn't rained in 2 months in California, so we're due for rain, so the chances of rain is higher. The probabilities themselves will not change based on past behavior. So anytime you read something like that, it is not true. It is stating that it's the law of averages when the law of averages does not exist. So nothing will be affected. The only time probabilities change is when you are doing things like picking a person. And now that that person is out of my sample space, my probability has changed because that person has left the group. So that is doing things without replacement. But this idea that they're referring to with law of averages is not that. It is basically saying because it hasn't happened in a while, the likelihood of it occurring is higher, which is not true. Okay, now this probability and frequency tables is stuff we've done before. It's a 2-way table. It's representing categorical data. And there are 3 types of questions they can kind of ask from this. They can ask joint relative frequency, marginal relative frequency, and conditional relative frequency. And I'm going to kind of remind you of what those 3 things are. So what is the probability of picking a male whose favorite leisure activity is dance? So one thing I'm going to point out first, because I'm going to use this, we had 2 notations. One was for and, the other was for or. And is where both things have to be true at the same time. Or was when it could be A, it could be B, or it could be A and B. So basically, as long as one of them is occurring, it's true, it's valid, we say it works. So in this case, we want a male whose favorite leisure activity is dance. So this is going to be an and statement. So what we refer to this as is a joint relative frequency. And for joint relative frequencies, we're going in, and I'm going to use the notation male and dance. The table total ends up being our denominator, and the numerator is just going to be the intersection of the 2 categorical variables you're interested in. So since I want male and dance, I'm going to where those 2 things intersect, and I'm going to get 2 out of 50, which is 0.04 or 4%. If your denominator is 50 and you have to convert to a decimal, all you have to do is multiply times 2. Little fun fact. What is the probability of picking a person whose favorite leisure activity is reading? So in this case, this is what we refer to as a marginal relative frequency. And basically for marginal, it focused only on row column totals. So this is one of those questions where it was tricky because sometimes they'll just say, what is the marginal relative frequency of reading? And it's a very, like, they're trying to see if you know the vocabulary, but it's not a hard question. So I'm going in, I'm doing reading, and I'm going to, with marginal relative frequencies, your denominator is still the table total The only time it changes is if you have a conditional. And then all you're looking at is the read column and the total number of people in that column. So 16. 16 out of 50 is 0.32 or 32%. And so to kind of go in and use a complement with our marginal relative frequency, it says, what is the probability of picking someone who does not consider dance as their favorite leisure activity? So when I write my probability statement, I'm just going to say not dance. You could also do dance with the superscript C, and that's dance complement, but personally, even I just go in and write not this. So there's two ways you can do this. You could go in and you could add up the other columns, the column for sports and the column for reading, and divide it by the table total. I'm going to use the complement formula, and I'm going to do 1 minus the probability that they do like dance. So that's 1 minus 18 over 50, which ends up being 64, I believe. Let me double check. Yes, 64. Now, if I were to go in and do it the other way and take the 16 from sports and the 16 from reading and divide that by 50, I'd get 32 over 50, which is also 64%. Again, how you do it is completely up to you. It is your preference. Both of them would get you full credit on a test. But how you approach it, your option. Okay, so that one was another, I would consider this a marginal question. And then the last type you will see is a conditional. Now, basically, when we referred to conditional probabilities, we said that now that I have this sample space has been altered. So in all of the others, in the joint and marginal, the sample space was all 50 people. Now they're saying, given that you've selected a female, so now I'm not looking at every single person in this 50-person sample. I'm focused solely on the 30 females that are in the sample. That is my condition. So there is a specific notation that we use for this. We go in and we say the probability of, and there's usually a vertical bar. That vertical bar is going to represent the word given. Now, a lot of people get confused with why it's written in the way it is, but basically the probability that you're most interested in is going to be the first one that you read. And so since we are most interested in what is the probability she likes reading, that's overall what I'm looking for. That is the word that we write first. And the given, the condition that you have, is going to be how your sample space has changed. So instead of looking at everyone in the table, I'm focused solely on the females. Now, I also like to think of it in a way where the denominator is going to be, it almost looks like it's under the fraction bar, the second part. So we said there's 30 females total, and I'm interested in the probability that she likes reading. So in my row of 30 females, I just need to see how many of them like reading. 8 of them do. And so that's going to turn into 0.667. And then the same thing could be said, 26.67%. So be very, very careful. I will say the common problem that people get confused is the conditional. Usually they use the word given, or they'll say something like, if you have selected a male, or what is the probability of them liking reading given that you've picked a female? The language of the question has changed slightly, but it's not always this is a conditional statement. You need to make sure you change the denominator. Just be very, very careful for those. Okay. Any questions on our table stuff? We did this stuff all the way back in Unit 1. Truthfully, probably like 1.1, like maybe one of the first lessons we did. Okay, last bit is something that is carrying over from Unit 3. We've already discussed simulations. Basically, think of, okay, I want to know what's the likelihood of me winning a prize out of a cereal box. I'm not realistically going to go out and buy 10,000 cereal boxes. I'm going to simulate the chance of, if there's a 50% chance of me winning, how often do I actually win? And we do that with simulations. We try to run it through a computer and see if this was truly random, how likely is it for something to occur? Now, in the write-up of this, a lot of it looks similar to what we do in experiments and sample surveys. This is one where I will say it's not guaranteed, like for the experiment and the sample surveys, it's probably guaranteed you're going to write up some type of design for that. This is less likely, but I'm still going to kind of show you what to write. It's less intense than the experiment and the sample surveys. So usually you want to go in, you want to identify your probability that you're trying to find. And then we kind of go in and we plan what we're going to do, basically describe how you're going to use your chance process. We do that by talking about the tools, how are we assigning values, how many values are we picking, how many times do you run the simulation, and then what are you recording? Of course, repeat digits and things like that. Again, this is less intense. You'll see why it kind of changes a little bit. Usually, if this is a question on the AP exam that you get, the tool that you're going to end up using is a random digit table. I know we didn't do a ton of work with this in the sampling because realistically, you're probably going to use a random number generator or the hat, either one. The reason why they would do this, if you think back to the day we started talking about these, we did a simulation where we were trying to select people to be a part of our sample survey, kind of. And we used the random digit table to kind of select numbers. Those numbers were picked with and associated with a hotel. Once you have kind of a plan, usually if this were an AP question, they're going to actually have you do the simulation. So they'll have you select the numbers from a digit table that they've provided you with. And at the very end, you want to make sure that you are answering their question. And a lot of people seem to forget that after they've gotten through all of the other steps. So we're going to kind of talk about a basic example of how simulation could work. You've actually done some simulation type things in your math labs already. If you think back to the driver's license problem of like, did they pass on the first test? Did they pass on the second test? That's a simulation. It's just, it depends on how many people you're selecting and in what context. So let's look at this. What is the probability that a student gets 6 out of 6 questions correct on a true-false quiz written in Greek? And we're going to assume that the exam taker does not know any Greek, and should the instructor be concerned about cheating? So to give a little more context so it makes a little more sense, say for instance, this instructor has given this quiz and he's worried that his kids are cheating because they got 6 out of 6 right. So someone gave them the answer. Someone said, these are the answers for the true-false quiz. And so he kind of wants to see how likely, if this was truly random, because that's what guessing is, truly random, how likely is it for them to get 6 out of 6 correct? So it's called like state your thing. I call it kind of like, what's my objective? My objective is to kind of answer the question, how likely is it to get 6 out of 6 correct on a true-false quiz if completely guessing? Okay, now, just to kind of frame this in the context of true-false. True-false has 2 possible answers. So on a true-false quiz, there's a 50% chance of getting it right and a 50% chance of getting it wrong. Because true, false. One of them is right. Complete guessing. So we want to see if like we were to simulate taking this quiz and guessing, how many of the questions would we end up getting correct? So I'm going to kind of go in, I'm going to do my plan of action. This is going to look similar to our experimental design. Now, if I have a 50-50 chance, usually I told you if you have 10% markers, so this is a 50%, which is a 10% marker, I don't use double digits. I'm going to say assign, I can do little bullet points, assign 0 to 4 to be correct. We'll say right, since I use that. And 5 to 9 to be wrong. So when I read this random digit table, if I see the number 0 to 4, that means they got the question right. If I see the number 5 through 9, that means they got the question wrong. So 50-50 split of my 0 through 9s. For a random digit table, it has to be all single digits or all double digits or all triple digits. You have to kind of be in the same family. Then I'm going to say use random digit table to select a single, let's do 6, to select 6 digits. Repeats are okay. To represent one quiz. Let's do 6 single digits. Now, the reason why I pick 6 digits as one quiz is because there are 6 questions on this true-false quiz. So again, just reading through, I assigned my numbers. I'm going to use a random digit table to select 6 single digits. Repeats are okay. Now, if you were selecting people, generally you don't want to pick the same person twice, which is why we kept saying ignoring repeats, unique numbers. In the case of picking whether it's right or wrong, you can pick the number 2 twice and have 2 questions correct. So it is okay to have repeats in this case. I am going to then record how many questions are marked right in my 6 questions, in my 6 digits. Then we'll say repeat for, I did 20. I actually ran this simulation for us so we can have some data to kind of actually look at. But basically, we're going to repeat this process 20 times. So 6 trials or 6 digits, and then of those 6 digits, they make up 1 trial. We're going to do this 20 times. So to avoid having you have to actually do this, because we've done this before, I'm going to go into like my do category. So when I went in Thursday night, because I did this before A-Day, my first trial, looking at a random digit table, I had 4, 5, 9, 1, 2, 7. So when I look at those numbers, remember 0 through 4 represent getting it right, 5 through 9 represent getting it wrong. So this would have been right, this would have been wrong, wrong, right, right, wrong. And so the part with simulations that people struggle with the most is what am I actually interested in recording? And I want to see how many are they getting correct. So yes, these numbers are important in terms of like assigning right and wrong, but the only thing that's going to get recorded from this trial is the number 3. because in this trial 1, they got 3 questions correct. So I did this again and again and again and again. And so I have a table where I listed the number that they got correct and the number of trials when I did my 20 that actually ended up having that many correct. So if I have 6 questions, they have the option of getting all 6 right, but they also have the option of getting all 6 wrong. So they can get 0 correct all the way down to 6 correct. And when I did this, the numbers that I came up with were 0, 2, 3, 8, 5, 2, 0. So just again to kind of talk about variability, this is the sample that I got from the random digit table I was looking at. Every single stats textbook, or even like online, you can go to random digit table and there's probably like randomdigittable.com and it's just a list of random numbers. So I pulled one from one of those random websites. I went in and this is the sample I collected. That's not to say that if I went out and I told you guys to do this sample yourself, that you're going to get these exact same numbers. The left column should be the same because those are the only outcomes that are possible, but the right column would differ based on the numbers that you're looking at. So when I go in, the only thing I really care about from what I have currently is this 6 row. So when I went in and I did this, the 6 out of 6 correct, there is a 0 out of 20% chance that this happened due to randomness alone. So based on what I have, that's all I can expect to see. Like just purely random numbers I was looking at, there's a 0% chance of it occurring. So remember, our threshold was 5%. If it's below 5%, we say it's unusual, we should be suspicious, we don't agree, we think they're lying, whatever the question is phrased as. And in this case, since it's 0%, I'm going to go in, I'm going to conclude. I'm going to say, according to the simulation, because again, this is my simulation. That doesn't mean that if I weren't to do another one, that maybe I do get 6 out of 6 correct. And which is why most likely whenever people actually do simulations for real things in the real world, they probably do more than 20 trials. They do like 1,000, 5,000, and they run it, and they have computer systems that run it for them. So according to the simulation, there is a 0% chance of getting 6 out of 6 correct on the true-false quiz by guessing alone. So the instructor should be, what is the language they use? Concerned about cheating. Again, the biggest mistake that we see for if you were to get an FRQ with like this, which I again think is very low on the totem pole of things that they want to ask, is that conclusion at the very end, where you go in and actually answer what they are interested in. So we do think that the instructor should be concerned because his student got 6 out of 6 right, and there's a 0% chance of getting 6 out of 6 right if you are just completely guessing. So what you guys will have today is your